Hey, SM3, no, SM2. We are going over 10.4 this week and a little bit of 10.5, but we're going to do it all in one lesson. But there will be two videos for it. So in 10.4, we're talking about inscribed angles and polygons that are in circles. So still in the realm of circles for today. But first, let's cover some definitions first, okay? So, inscribed angles and intercepted arc, what do those mean? So, over the last couple times, we've learned about chords, right? So, here was a chord right here, and a chord with, like, here, point A and C, well, made an arc, okay? This was the minor arc, if you guys remember that. But then, last time in 10.2, we talked about central angles. So, central angles, let's say that we had a center here, okay, and central angles were angles with the vertex at the center. So this was the central angle, and you can see here that the sides, let's call this P, so AP and CP, again you can see that this angle with these intercepts create another minor arc. Okay. Now today we are going to talk about inscribed angles and intercepted arcs. Okay, so an inscribed angle is an angle. So inscribed angle, an angle whose vertex is on a circle, and whose sides contain chords of the circle. And so basically, and the sides are chords. So pause the video if you need to finish writing down that definition. But here you can see that we have a angle, and the angle is on the circle. Now from here, A to B and A to C, this creates a chord. This is a chord and this is a chord right here, and then you can see that we also have created this minor arc from this angle. And this is what we call the intercepted arc. So an arc that lies between two lines, rays, or segments. So intercepted arc. So an arc that lies between two lines, rays, or segments. Okay, so this is the intercepted arc right here, and it's also a minor arc, right? Okay, and so here's what we know about intercepted arcs and inscribed angles. Okay, there's actually a pretty cool relationship between the two things. Okay, so in this theorem, measure of an intercepted angle. So this angle right here, what is the measure of this angle? So the measure of an inscribed angle, if I said intercepted angle, I meant inscribed. So inscribed angle is 1/2 the measure of its intercepted arc. Okay, so this angle right here, so the measure of angle ADB is equal to half of its corresponding intercepted arc, so arc AB. Excuse me. So right there. So this angle is half of this arc right here. Okay? So that's its relationship, 1/2. So let's look in this example and see how we can apply this theorem and the relationship between intercepted arcs and inscribed angles. So measure of angle t. What is the measure of angle t? Well, we see that its corresponding intercepted arc is 48. Okay? It is 48. And we know that this angle right here is half of this angle, this arc right there. So measure of angle t has to be 1/2 of arc RS, which is 48 degrees. So it has to be equal to 24 degrees. So that's measure of t. Now B, measure of arc QR. So let's first note where that is on the circle. So that's right here. Okay. Now this doesn't have any inscribed angle, right? I don't see an inscribed angle anyways. So let's look at information that we have elsewhere. So we do have this angle right here, which is 50 degrees. And this angle has to be double it. Okay? So I know that this angle has to be 100 degrees. Because that's the relationship between an intercepted arc. That's intercepted arc and inscribed angle. The relationship is half or double depending on which way you're looking at it. Now also notice that this TR is the diameter because the chord runs through the center. So that means the angle of a semicircle is 180. If this portion right here is 100, then this portion has to add to be 180. So QR has to be equal to 80 degrees, because here would be 80, here would be 100, and together it would be 180 degrees. Okay. Find the measure of an intercepted arc. So this one should be pretty much the same. So it wants to find the measure of RS, it wants to find the measure of STR, and what do we notice about the two? So arc RS. Let's first identify where that is. So there is arc RS. Now this is an inscribed angle for this angle right here, but also notice that it is an inscribed angle for these two sides right here. So these two sides share the same inscribed angle. Okay? So if this is 31, well, this one has to be 62 degrees. This so measure of arc RS has to be equal to 62 because this angle right here is 31. Now, because this angle is 62 and angle T right here, or STR, so measure of angle STR also has to be equal to 31 degrees because you can see that it has an intercepted arc of 62 degrees. So what do we notice about angle STR and angle RUS? Well, they are congruent. They are congruent. This follows directly into this theorem right here, inscribed angles of a circle theorem. So all this theorem pretty much states is that if two inscribed angles of a circle intercept the same arc then the angles are congruent. Okay, if two inscribed angles of a circle intercept the same arc, then the angles are congruent. So you see here we have DAC. This angle right here, this inscribed angle, has this arc CD, but you can also see that the inscribed angle DAC shares that same intercepted arc. So that means angle ADB has to be congruent to angle ACD. Okay, so let's see how we can use that in this theorem right here, or in this example. So given that measure of angle E, right here, is 75 degrees, find the measure of angle F. So right here. Well, first thing I notice is that angle E, right here, has this inscribed, or has this intercepted arc GH. And I can also see that angle F shares that same intercepted arc. So that means that measure of angle E is equal to measure of angle F. Measure of angle E is 75 degrees, so measure of angle F is equal to 75 degrees. Pretty straightforward. Alright, now let's try this example right here. And this one will again lead into the next theorems, or they should anyways. So use the diagram to find the indicated measure. So measure of angle A. Okay, so measure of angle A. Now angle A, notice that this right here, we have ourselves a triangle. Triangle ABC, right? Now we don't know whether or not it's a right triangle at the moment. However, look at the hypotenuse here. So B to C, or the longer side of this triangle, I guess we should say, because we're not sure if it's right, but BC is a chord of the circle and it runs through the center, so by definition BC is a diameter. Now if this is a diameter, that means this length of this chord, or this arc right here, is a semicircle, so it's 180 degrees right here. And if this is 180 degrees, notice that this arc is an intercepted arc of the angle of sides AB and AC. Now thinking of that, if this is a 180 degree arc, that means angle A, which is its corresponding inscribed angle, has to be 90 degrees, which makes this a right angle. So measure of angle A has to be 90 degrees. Now if it's 90 degrees, then that makes this triangle a right triangle. Okay, that will help us with the rest. So measure of angle C right here. Well, I already know this angle right here is 28, right? So I know that this angle and this angle are complementary. All the angles here have to add up to 180, and since this is 90, that means angle C and angle B have to be complementary. So let's take 90 and subtract 28 degrees from that. So 90 subtract 28, and I get 62 degrees. So that right there is the measure of angle C. Okay, now it wants us to find the length of BC. So the length of BC, you could use the Pythagorean theorem, because we know the side lengths of the legs of the triangle, or what I would rather do is just perform a trigonomic function. So I could say, let's say I want to find sine of 28 degrees, which would be equal in this case to the opposite side, which is 3.9, divided by BC, which is the hypotenuse. Okay, and then if I set this up right, if I do my algebra right, BC should equal 3.9 divided by sine of 28 degrees. So 3.9 divided by sine of 28 degrees, and I get 8.3, we'll call it 8.3. So 8.3, yep, that should be the measure of that. Measure of AC, so right there, now look at here, its corresponding inscribed angle is 28 degrees, so this has to be double of that. So we do 28 times by 2, so that should be equal to 56, I believe. And then measure of AB right here. So I see that this is the intercepted arc of angle C, and we know angle C is 8. So AB, right? Am I looking at that right? So, angle C is not 8.3, this is 62 degrees. Okay, and so this is the inscribed angle for this arc right here, so it has to be double that. So 62 times by 2, which is equal to 124 degrees. Okay, and there you go. And then for this one, I think you guys, we can go over it. So name two pairs of congruent angles. Well, I notice here that this angle right here would have to be congruent with this angle right here because they share an intercepted arc. So let's say angle ABD is congruent with angle ACD. Okay. Let's see, BAC. So BAC, okay, this one also has shares an intercepted arc with this angle right here. So we could say that angle BAC is congruent with angle C or BDC. Okay, so those are two pairs of congruent angles. Okay, now let's talk about inscribed polygons. Okay, so an inscribed angle just means the angle is on the circle. So an inscribed polygon, well, a polygon is inscribed polygon when all the vertices are on the circle. Okay, so a polygon is it's a shape with angles and sides, right? So an inscribed polygon is a polygon with all vertices on on the circle. So they all have to lie on the circle. So if I have a circle here, okay, so here's my circle. So so here's my circle. So if I have a polygon, like let's say I have a quadrilateral. Okay, so a quadrilateral would have to be its vertices on all four sides. Not the best looking quadrilateral, I admit, but or you can have even something like a triangle. Okay, so a triangle like this. Triangle is also a polygon, something like that. Like this. This would also be a triangle. And then you would also have something like you could have like a pentagon, something that's five-sided. Okay, so these would be inscribed polygons. They just have to have their vertices on the circle. Okay, inscribed right triangle theorem. So if you have a right triangle in the circle, so this is what this theorem states, and we've actually already gone over this theorem in this problem. Okay, so if we have a right triangle inscribed in the circle, so this triangle right here is inscribed in the circle. All the vertices are on the circle. Now this specifically was a right triangle, and we found it out to be a right triangle because the hypotenuse was actually the diameter. And that's pretty much what the right triangle, inscribed right triangle theorem states. This one says that if a right triangle is inscribed, so if a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. Okay, That's pretty much all it really says. Or basically, it basically just the opposite is also true. So basically, if one side of the inscribed triangle is the diameter of the circle, then the triangle is a right triangle, and the angle opposite is a right angle. Okay, so if a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. Or if you have, let's say like right here, if you have a diameter, then its corresponding um, inscribed angle has to be 90 degrees, right? Okay, so that's pretty much it right there. If you want something a little bit more equation-like, so measure of angle ABC. So that's measure of angle ABC. So in this diagram right there, this has to be equal to 90 degrees if and only if AC, so this line right here, is a diameter of the circle. Okay. And then, so that's for triangles, right? Triangles. It's not not necessarily for any triangle, just for right triangles, right? And then the inscribed quadrilateral, so if we have a quadrilateral inscribed in a circle, so a quadrilateral quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So pause the video if you need to go over that or write that down. But a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So here in this circle right here, we have an inscribed polygon because all four angles are on, vertices are on the circle. And what this means is that the opposite angles have to be supplementary. So angle D and angle F, if we add these together, they have to equal 180. And then angle E and angle G also have to add to equal 180 degrees. Okay, so let's put these theorems to the test. So find the value of each variable. So in A, we want to find the variable x. Now notice that this is an inscribed triangle, and notice that the triangle right here, one of its sides is a diameter. Now if one of its sides is a diameter, then that has to mean that it's the hypotenuse of a right triangle. So this angle has to be 90 degrees. So 2x has to equal 90 degrees. Well, then in that case, if I divide by 2, x has to be equal to 45 degrees. For B, remember that opposite angles, this is a quadrilateral. Quadrilateral is a four-sided polygon. So because the vertices are on the circle, it's inscribed, which means we can use the inscribed quadrilateral theorem, which says that opposite angles are supplementary. So angle E and angle G have to add to be 180. So angle G, which is y, so y plus 120 has to equal 180 degrees. Subtract 120. Subtract 120, so y has to equal 60. And then same thing for these two angles, so D and F have to equal 180. So we could say Z plus 80 has to equal 180. Subtract 80 from both sides, and in that case Z has to be equal to 100 degrees. Okay, and that should pretty much do it. So for these notes, here's some extra problems I encourage you to go over on your own. Set it up the same way I did here, just know you might need to do a little bit more math, but probably not that much. But just find the value of each variable stated in each example, just using these two theorems that we know right here. Okay? Alright, and that should do it for 10.4. Make sure to go to 10.5 for just one more concept.